What we're doing for the rest of the semester is we're going back through image quality or image creation. We're going to cover it twice. So instead of going with individual chapters, like what we did in the second semester, it's just kind of we're going to go through all the chapters that touch image creation. So that's going to be, all these chapters here. We're going to start with image quality, and then we're going to go through, obviously image quality, into resolution, different types of resolution, dial those in, quality control. We're going to sprinkle that throughout. So then we're going to get into chapter 12, image capture, what it is that happens whenever, we make an exposure, and so on and so forth. So we're going all the way through what we talked about in the second semester, and we're going to do it twice. So we're going to go all the way through it once, and then we'll have a test on it, and then we're going to go back through it and have another test. So that second test depended on where we are in the semester and how long it takes us to go through this the first time. It may wind up being our final exam, so that we don't have two more tests and a final, just one more test and a final. So we'll see. We'll see how things go from this point forward. So the first time we'll go through this, it's going to be pretty meticulous. It's going to take us a while. The second time is just maybe 2 weeks. So the second time is going to be pretty quick. It's almost more like a review of what we did the first time around. So just getting started with it. So image quality is just accurate representation of the size and shape of the anatomy or the structure that we're trying to look at. So we're going to talk about different types of distortion and different types of resolution. And the sharpness, spatial resolution, is the first thing we're going to talk about. Spatial resolution is the sharpness of the image, the lack of fuzziness. There's a fidelity. Sometimes you'll hear the wording sort of like this: the fidelity with which the structural integrity is represented. So it's the lines and what the interface in between two contrasts look like. So you got contrast resolution, you got spatial resolution. And spatial resolution is that line at the difference in those contrast levels. Contrast is whether or not you can see black and white, as opposed to the spatial resolution is what does that line where those two things separate, what does it look like? So how we test for spatial resolution, we'll take a look at too. All right, so image quality, again, representation and anatomical density. We got contrast resolution, that is how well we can see the difference in tissue densities, as controlled by a number of different things, primarily the computer algorithm, but we do have some differences, as we saw this morning with our technical factors. Within a diagnostic range, within a reasonable range of KVP and mass, then there should be minimal difference. Our computer algorithm should pick that up and even out those density differences, or not even them out, but I guess a better way to say it would be accentuate those density differences so that we have better contrast, right? But equipment use, that will be our use of grids to absorb scatter radiation. Remember, the scatter radiation is a unwanted density. It's a density, but it's unwanted density. If we can remove that, then it brings out that contrast. Then our patient factors, certainly. What's going on with the patient? Are they full of fluid? Are they normally full of fluid? How much soft tissue do they have? What disease processes might they have? Things like osteoporosis and all that. So we'll talk more about that as we go through. So resolution, definition of resolution. I'll let you read through that, but basically it's the ability to see two things as different things. So if the line in between those two things is fuzzy and you can't make it out, then you have low resolution. Now, resolution, whenever we say resolution, there's contrast resolution, there's spatial resolution. Spatial resolution is what we're talking about most of the time when we're discussing resolution. Generally speaking, if if I give you a question on contrast resolution, contrast is always going to precede resolution. So if contrast is not in front of resolution, you have to assume what I'm talking about, spatial resolution, sharpness, or reported detail. Okay? So contrast resolution just means contrast. Resolution in this context means the sharpness of those lines. How well defined are those lines? Are they fuzzy? Are they clear? Can you see the trabecular markings? Can you see the cortex of the bone? Is the patient free of motion? Right? All of those things. Okay, so measure sharpness of the image or the fineness with which you can make out those small structures. So again, we've got spatial resolution, we've got contrast resolution. Spatial resolution is the sharpness of actual recorded detail. It's the actual lines, but it's also the absence of noise that would cover up those lines as well. In this context, we've got spatial resolution, we have sharpness of recorded detail, and we have visibility as well. So don't confuse those two. Visibility reported detail involves fog, whereas spatial resolution, the noise they're talking about here is quantum model. That's recorded and it's still covering things up, right? But when we're talking about other noise like fog, we're talking about the inability to see the resolution that we actually record. So that's fog, and that's a visibility issue. And we'll clean that up, with proper technique and use of grids if we need to. So spatial resolution is expressed by the number of line pairs per millimeter, and that's what this is a line pair per millimeter test tool. And as you would expect on this, the higher the resolution, the skinnier the lines get to. So the higher the number of line pairs that you can visualize, the higher your resolution. So if we can see all the way down to the bottom of this thing, still separate the individual lines. First off, your eyes are really good. And secondly, our recording media would be, high resolution. So the lower the resolution, just look at this and let your eyes go out of focus, cross your eyes just a little bit, it goes fuzzy and you lost resolution. So fuzziness is lack of spatial resolution. Spatial resolution is how fine the lines can you see? Can you see those trabecular markings in the hands, in the bodywork? Can you actually see them? Or does it just look like you got some fuzzy cortex and then you got the dark area in between inside the medullary cavity or where the trabecular markings should be? So spatial resolution, sharpness of recorded detail, okay, as opposed to contrast resolution. So the ability to, and this is another way that questions will come to you, is the ability to resolve and render the fidelity of those lines, whether or not you can not just record them, but display them as well. So in our current systems, we got a lot of things going into spatial resolution. So we've got we've got the positioning things that we've talked about throughout the curriculum, OID, SID, those things that can affect it. But we've also got the image receptors. So our image receptors, our current image receptors, are made up of kind of like individual little pieces, individual small image receptors. And the more of those that we have, the sharper the image. And it's kind of like a TV. With a TV, how do you measure resolution in television? Or a computer screen, your phone. Come on, y'all know this. You got two sets of numbers, right? Two sets of numbers that basically give you a number of pixels in one dimension versus a number of pixels in another dimension. And your image receptors are basically the same thing. So you've got, the larger the number in your image receptors, the higher your resolution. Like TV, if you had a 480 by, what's the other number? 480 by I don't know, 720 or something like that. Is nobody buys those things anymore because they're low resolution. What do you buy now? It's like, 5,000 by 7,000 or something like that, right? And then in those, it almost looks like you can walk into your TV. So the higher the number of those individual things, the higher the resolution. But it's not just dependent on that. So we've got the equipment issues that we've talked about before with SID, OID, focal spot size. But we've got an issue with our image receptor, and then that's not everything that goes into, it certainly goes into recording, but not display. Have you ever been back to the radiologist's office and looked at the computer monitors that they read off of? They look anything like the ones that you read off of in the Lightroom? No, very high resolution, as they well should be, right? So the image that you see is low resolution, even though you might have used small focal spot, low OID, and long SID on high resolution image receptors. Your image display is not that good compared to the radiologist. So it's not just being able to record, but also being able to display that high resolution that gives us a special resolution. Record and render. Okay, so in your imaging systems, you may be familiar with this, you may not be familiar with it, but we've got a lot of test tools in the imaging system that you can test for spatial resolution. They've got diagrams, or not diagrams, but test patterns that are loaded into the computer system that will show you what the resolving power is of the display system. Also, though, you've got some other things that you have to make exposures of to, like your line pair per millimeter test tool. So you've got a number of different things that you have to test. This tests two things, essentially. One is your X-ray tube, is your focal spot giving you what it is your focal spot's supposed to be giving you. That's number one. Number two is your image receptor recording what it should be recording, right? So the things that can affect your focal spot size, your actual focal spot size, one of those things will be the effectiveness of the focusing cup. What does focusing cup do? Make sure that they stay together. Right, it mashes the electrons together so that whenever they go across the tube, they're all negative charges, right? So if they're all negative, they're having a tendency to want to push each other apart. But the focusing cup crams them all together so they hit a specific portion of the anode, focal tract on the anode. And if we lose that charge on the focusing cup, then the electrons go everywhere and focal spot size can increase. Blooming issues, if you're holding the rotor down, that's not really a QA issue as much as it is a operator error issue. But anyway, this will test not just the focal spot size, but also test the image receptor as well. The display is kind of loaded into the system. You can bring that up and take a look at it and see what your display looks like as well. So with quality control, we're going to test everything. So in quality control, just real quick, you got a number of different tests for quality control on your machine, and you're going to test everything on it, really, not just your spatial resolution, but you're going to test your MA, your time, your KVP, your perpendicularity, how perpendicular is the beam to the image receptor, or is it just kind of tilted off a little bit? So you're going to test a lot of different things, and those are going to be periodic. Most of the time, you're going to test them once a year. The first QA test is going to be right after you get the machine. That's what we call acceptance testing. So we actually got a grant, and our X-ray room is supposed to be replaced. We're starting to have some problems with it. You may be familiar with that. The table has been kind of quirky for about a year now. The computer died about a year and a half ago, and we had to get it replaced. And our budget, departmental budget just doesn't pay. We don't get that much. The last repair on the table, I think we spent something like $8,000 and it's not fixed. The computer was about $30,000 and they're never going to give me that much in my repair budget. So it's expensive to fix it and we're starting to have some problems with it. So we got a grant to get it replaced, but it's probably not going to happen until probably Christmas, maybe. And then once they put it in, what they're going to do is they're going to run some tests on it. And they're going to test everything. Is it shooting with the right KVP, MA, or the MA station's accurate, or the timer's accurate? Is the beam shooting perpendicular, or collimator's right? Everything gets tested, and then we sign off on it. That's what we refer to as acceptance testing. And then if we were in a hospital where we were making images on, people, live tissue, then every year they would have to come in and they'd have to test all that stuff over and over again. Every year, at least once a year, they would have to test it again. Okay? Because your mass value, your output from your X-ray tube this year, today, on a brand new equipment, is not going to be the same as your mass value in a year. Why is that?
Added filtration.
Added filtration, tanning of the tube. Exactly. The more you use the tube, the lower your output's going to be. So they got to get in there and they got to tweak it so the output is the same. And at the same time, they have to test half value layer. They have to test everything to make sure that the output from the X-ray tube is reflective of what it should be to make an image on living tissue, right? So that's an ongoing process. So as long as you own that machine, every year a physicist is supposed to come in and test all that stuff. And we do have physicists come in and test our stuff, but it's not as frequently as what it should be in the hospital because we're not set up to shoot people. So that's the purpose for quality controls, to make sure that our X-ray machine is putting out what we expect it to put out. And the QC measures we're going to talk about throughout the semester, quality control on pretty much every aspect of the machine. Testing intervals, for the most part, is going to be every year. And then within each one of those tests, there are some allowances. For example, your collimated field, 40 inches, it can be off by a little bit more than an inch, so 0.8 inches. So it's 2% of the SID. Okay. So 2% of 40 inches is 0.8 inches. So your collimators can be off by about 0.8 inches. So what's your rule for collimation? How close do you collimate?
Within an inch.
Within an inch of the anatomy. Why is that? Because you got a variance on your collimation. Remember, what you're seeing, is just a reflected light field, and it's not necessarily reflective of the radiation field. So there can be some incongruity between the two. Also, your radiation field may not be represented well by that light field. So, your light should be reflected off of a perfect 45-degree angle mounted mirror, right? So your light's coming from here, X-ray beam's coming from up there. What happens if your light or your mirror slips a little bit? It's just not going to be lined up, right? So there are variances and allowances within each one of those quality control tests, and we'll talk about those as well. All right, so good programs, it's not, X-ray programs, it's good programs inside of the hospital start with quality, with repeat analysis. What's going on that's causing the most repeats? Is it an issue with is our biggest issue maybe our index number is off? Maybe not even leading to repeats, but is our index number off, consistently off? What caused that? Well, it could be that our phototimers, our radiation cells are inaccurate, not receiving the right amount of radiation before terminating the exposure. Are we setting techniques, in which case we need some education, on proper techniques? So, what's going on with it? Are we clipping anatomy? Is the anatomy that we're clipping strictly on one side of the patient, indicating the mirror might have fallen off? So we got to have some sort of analysis. The sticky thing here is, and you've probably seen this, what repeat analysis depends on is the integrity of the techs that are repeating the exams. Okay, so what happens in a lot of cases is you repeat an exam, and what happens to the image that wasn't any good? What should happen to the image that wasn't any good? It should go into some sort of repeat, folder so that they can assess what's going on, with individual exams while the exam was repeated. But where's it going most of the time?
And then
It's actually say delete, and part of that in a lot of cases is, the tech just doesn't want to hear about it. But in a lot of cases too, though, you find yourself in a situation where you're a hospital administrator, department administrator, your repeat analysis initially at least needs to come without any kind of punitive, you need the technologists who are submitting those repeats need to know that you're not using it just to fire, is where I'm trying to go with this. So if they think that it's going to be punitive, that they tell you what they're repeating on, then they're just going to delete all the images, right? So they've got to be able to collect that information. So they need you to, to turn that information into them. So you got your initial testing. We just talked about that. That's your acceptance testing. Then after that, it's going to be annually, unless there's something else, some other reason to do the testing. And then we've got the manufacturer's recommended intervals. Okay. So CR capture. We'll talk about CR capture first. Still testable, probably maybe until the next incarnation of the registry. It might come off. No screens of films on the registry anymore. Every now and then they'll go through the registry and they'll delete certain things. So we'll talk a little bit about CR, and we'll talk about you. So we've got in CR, we've got image receptors, we have CR readers, and we have the image display. So when we started this move into digital radiography, this is where we started, was with CR. And the reason for that is because the transition from screens and films to CR was a lot cheaper than what it was to DR. What we had with screens and films was a standard x-ray room, and you had all these x-ray films, and we had, in most hospitals, all the hospitals I worked in, we had what we referred to as daylight readers. Or daylight processors. So with a daylight processor, what you did was you took an image on an x-ray film inside of a cassette. You took that cassette out of the bucky, you took it over to the daylight processor, and you plugged the whole thing into the processor. It was light proof inside. It took it away from you, and it opened the thing up and took the film out, processed the film, put a new film in it, closed it up, and it gave it back to you. Okay. So with a DR system, when's the last time you had to take the image receptor out of the bucky in your hospital? Never, right? So with a DR system, what it does is it captures the image and it sends it electronically to some sort of gathering unit, and then puts that into the computer. So the technologies are like night and day. They're completely different, right? But with a CR, what they did was they replaced that daylight processor with what we refer to as a CR reader. They replaced the films with these CR cassettes. So the technology, even though it was night and day in image capture, is totally different. The way we used it was much more similar. So we didn't have to replace an entire room. We didn't have to set up the communications that would send the information from the image receptor over the computer. The only thing that we had to replace was how we read it and then we had these new cassettes that looked just like the old cassettes. So the process from a technology standpoint was identical. It was a seamless transition. The only thing that we had to do then was to figure out, how to use the computer. So it's a whole lot cheaper. Instead of replacing entire rooms, the only thing that we replaced were those two things, the image receptors and the readers. Instead of using films, we used, the CR cassettes. And daylight processors, we use CR readers. All right, so what we're going to talk about are imaging plates. We're going to talk about photodiodes, photomultiplier tubes. This is getting into DR. Photostimulable luminescence, photostimulable phosphor, storage phosphor, and then storage phosphor screens. All right, so in our image receptors in CR, what we have was a cassette. And in that, we had a imaging plate with photostimulable phosphors. We had two different types of phosphors. One was what we referred to as needle phosphor because of their construction was kind of cylindrical, tiny, but kind of cylindrical. And then we have what we refer to as powder phosphors. And that was more like, what would be a good analogy for that? I don't know. It's almost like a paste filled with individual little specks that we'll put onto the imaging plate. Okay, so the needle phosphors were kind of like, if I were to take all the pins out of this, they had a dimension to them, depth to them. So they were kind of like this. All right, so we got individual little bitty phosphors that have, kind of a length to them, as opposed to the powder phosphors were just these flat individual little bitty phosphors. Okay. So powder phosphors as opposed to needle phosphors. We'll just talk about it. So how plates would work is you got kind of like interactions inside the patient's body. And what you would get is as the X-ray beam interacted with the phosphors, regardless of what type of phosphors they were, you get excitation and a temporary ejection of an outer shell electron, which would drop almost immediately back into place. And what you would get in that is not just the stimulation of that phosphor. You'd get a little bit of a glow, not as much as an intensifying screen in screens and films, but you get a little bit of a glow, but then you would get some storage as well. All right, so you have a storage phosphor in this construction that raised the state of those phosphors to a state that we refer to as metastability. Okay, and metastability see if I can find it. A definition of metastability, maybe not. On a model, and not. So briefly, what metastability means is that you've got this image capture, you've done the exposure, and you got this image capture, and whenever the electron drops back into space, into a space, then you've got a truly stable atom. All right, so remember back to the first semester, you've got a couple of different things that define stability in an atom, right? If we have too many neutrons, the nucleus of the atom gets too heavy, and we've got radioactivity, and that's truly unstable. But anytime you eject, we should have the same number of protons as what we have electrons, right? And in that case, we have a neutral atom, which is also stable. Okay, so what metastability means is that you're stable in all of those things. You don't have too many neutrons, and you've got the same number of protons and electrons, but it's a higher level of stability. Okay, so, and by higher level, I'm not talking about a better level of stability. It's that it's stable, but it's holding on to some stuff that it otherwise would not hold on to. So it's got some energy. It's stored some energy. The thing with metastability is that it's kind of got a half-life to it. And what I mean by that is the problem with CR plates is if you're assigned to portables and you're in a big hospital that shoots a lot of portables, you know, you may have a stack of CR plates. You may have to go up to the floor, and it may take you a long time to take all the x-rays you need to take. And then you've got to come back downstairs. You got to feed those into the reader, right? Unlike the DR systems you're using now where you get the image immediately, these things had to go to a physical place to be processed. With that metastability, you know, as soon as you make the exposure, that's as good as the exposure is going to be. And if it takes you 2 hours to get back down to process that image, it starts to lose that metastability and the image starts to degrade. To the point that if you don't process the image within, I think it's 8 hours, that image is garbage, unusable completely. Okay. So metastability doesn't mean that it's a better level of stability. It just means that you've got something that's held on, you know, some sort of extra energy that it's holding on to. It's stable, but it's not at its most stable state. So what controls the sharpness in a CR system is the same thing that controls sharpness in your current systems, and that is the size of the phosphor. So if all your phosphors are big, like, you know, comparing, again, these needle phosphors, so to speak, if all your phosphors are large like this, then what that's going to result in is an image that's kind of pixelated. You know, if they were square, it'd be kind of pixelated, as opposed to if they're smaller like this, it would be much more sharp. So your phosphors are not square like a pixel, but the same thing still applies. The larger the phosphor, the lower the resolution. The smaller the phosphor, the higher the resolution. Also, though, the thickness of the phosphor layer. So the thicker the phosphor layer, and this doesn't really apply as much with needle phosphors as it does with the powder phosphors, but if you've got them stacked, right, the way that we capture the image and the way we release that and read it is that metastability, that energy is released in the form of light. So knowing what you know about light, if we're releasing light from deeper inside and we're trying to measure that, then it's going to be a little bit fuzzier and we're going to have a little bit of overlap between those phosphors that are deep and some other ones that are shallow. So what that means is the thinner the phosphor layer, the sharper the image. The thicker the phosphor layer, the fuzzier the image is going to be. And then we've got a reflective layer. So what we've got in the image receptors, CR image receptors, the construction is almost identical to the construction of an intensifying screen film radiography. So what you've got is this phosphor layer, and then you got a reflective layer, and then you've got a base layer. And just like emission of X-rays, the emission of light from those phosphors is going to be isotropic. So, and we'll talk about how it is that we release that later on, but it's basically a laser. As the laser hits it, that light wants to go off in all different directions with equal intensity. Some of that's going away from the reader. So in order to maximize the signal back to the reader and minimize patient dose, what we have is a reflective layer behind that phosphor layer. And with that reflective layer, if the light's going in that direction and it's spreading out, and it hits that reflective layer and it comes back, it's going to continue to spread out. And again, you're going to lose sharpness of reported detail. So there are a lot of things that can go wrong in the CR imaging system that will reduce the sharpness of reported detail. So how we maximize it? Small phosphors, thin layers, and, you know, preferably no reflective layer. So here we have it. So with screens and films, we've got this situation going on, but you know, it's kind of the same thing with CR systems. So what we have then is the smaller the individual phosphors and the thinner the layer, then the sharper the recorded detail. Again, measured in line pairs per millimeter. Okay. So I'm going to talk about scanning of the CR system, and that's the last thing that we're going to talk about. So when we make an exposure, and say this is my image receptor, this is my imaging plate. We'll put this into the CR system. The CR system takes it in, and just like screens and films, inside this controlled environment, minimal dust. What will happen is the system will open the cassette and remove the imaging plate, and then it scans it. So what we've got are two different things going on in the CR system. All right, so the travel of the plate through the CR system is one thing. And then we've got also at the same time, we've got a laser that is scanning the plate. Okay, so we've got a fast scan and a slow scan. The slow scan is travel of the plate through the CR system. And then the fast scan is the laser. So we've got a laser situated in one place, and it's just going up and down this thing at just a really fast speed while this is trying to go through at a really slow speed. The purpose of the laser is to release that stored energy of the metastability and return the phosphors to their most stable state. Okay, so release the energy. The problem that you run into is a number of different things. First off, your laser, the width of the laser has to be consistent, and it has to be very small. All right, so preferably what you want to do is you want each individual phosphor to have its energy released at the same time. If you release the energy out of two of them at one time, then the light tends to blur together, right? So you need a very fine, focused laser. But the laser is going to be in one spot, right? So it's going to be in one spot. And so as it pivots, it's in one spot and it just pivots back and forth like this. It doesn't just travel up and down, would be less efficient, but it pivots. All right. So what happens, say I've got it situated right here. What happens to light as it travels? What does it do? We got a word for it. The X-ray beam diverges, right? So what happens to the light here versus the light there? It diverges. So we have to have some focusing optics to make sure that it remains the same. Failure of those focusing optics, we lose sharpness of reported detail, especially on the lower portion of the image receptor. Okay, so that's number one. What if our laser, maybe it's not stable and it's shaken this way while it's pivoting this way? What's going to happen to the phosphors away from the place it's trying to focus?
They're releasing energy.
They're going to be lit up too. They're going to lose some of their energy. And again, we've got bleeding of light and blending of light. It's going to be a fuzzy image, right? Also, what if we're scanning real well, and this doesn't really have that much to do with sharpness of reported detail, but what if the travel of our plate is inconsistent? So the ideal travel may be, this fast, and all of a sudden it slows down and then it speeds back up. What might happen then?
It's reading those different phosphors too many times.
You're going to have different intensity or different release of the energy of the individual phosphors, so that you're going to have this darker area in the center of your image, right? So a lot of things can go wrong in the scan phase. Travel of the plate is a slow scan, travel of the laser is a fast scan. And what we have to have in each one of these is consistency. So it's got to be consistent in its travel. The travel of the laser has to be consistent, and it also has to be controlled and stable, right? So it doesn't shake around. It's got to be focused, so we have to have focusing optics to make sure that it doesn't spread out, so that the width of our laser remains consistent across the image receptor. So a lot of different things going on with our CR reader. Let's talk about that. Read cycle. So what we have going on with the read cycle is we've got two things going on. We've got stimulation of those phosphors releasing the light, but we've also, at the same time, we've got light detection. So we've got two things going on. We've got this light detector with photomultiplier tube, and we get the release of the light, but we've got to pick that light up too, right? So we've got detection at the same time as stimulation, and then we've got to amplify that with the light in our photo multiplier tube. So we've got light collecting optics to pick up all that light that's let out of the phosphors. We're going to convert that from analog to digital signal. Sampling is an interrogation of the phosphors and measuring of the light that's released. And quantization is giving digital values to that based on how much light comes off of those individual phosphors. So that's where you get your contrast, essentially. You know, you got your bone, you got less light coming off of the bone as opposed to the lungs. So it's giving it a value to indicate lungs versus bones. And the last thing in the process of reading those plates is what we refer to as a eraser. An eraser is where we've got a bank of fluorescent lights that are really, really bright. So the last thing that the plate goes through is it goes in front of these fluorescent lights that shine on it, and it releases the rest of the metastability, returns all of those to the phosphorus to their most stable state. And the problem that we have in our QA of our reader is not only all the stuff that I talked about before, you know, the focusing optics, if they're inaccurate, you're going to lose sharpness reported detail. If you got dust on the lens, you're going to lose some contrast, probably some sharpness reported detail as well. But in eraser, we have a very specific thing going on. And if we've got lights that are burnt out in our eraser bank, then it's not going to completely erase that image, the previous image, and then we get what we refer to as ghost imaging. Okay, what a ghost image is you make an exposure. Let's say you make an exposure on somebody's head, right? You got a skull. You send it through the reader, and then you go do a pediatric chest X-ray with that same smaller image receptor. And so you get this chest X-ray with a skull in the middle of it. It's a faint skull, but it's there, right? So that's a ghost image, and that's an indication that you've got burnout lights in your eraser bank. And until I think it was year before last, I considered this strictly a CR issue, okay? Until, like I said, and it was reinforced last year. I think year before last, I think Caleb showed that we can have ghost images on DR systems, and he proved that in our lab. All right, so he took an X-ray of very high exposure with metal, and you know, for a few exposures after that, we'll wind up with metal. We could see what it was, you know, in that image. Who's at UT North? Okay, so talk to him about what Jeremy did last year. He completely shut down a room for about an hour. He again made an X-ray of some sort of big, thick bolt, and he used very high kVp, very high mass. He was trying to prove penetration. He couldn't get through this thing, but he made an exposure on this thing. And for about a half an hour, they were making exposure after exposure after exposure because he burned that into the image receptor. And every image that they took after that, it had that bolt in the image. So it was ghost image. I had no idea that you could, you know, ghost in an image on DR systems, but you can. So, you know, in your experiments this semester, don't do that. I understand they were pretty upset with him. He shut down their best room for like an hour, something like that, because they made exposure and, chest x-ray, and there's a bolt in the middle of this guy's chest. So they made another one. There's still a bolt in the middle of his chest, so they had to shut it down and just make exposures until that blended in and went away. So ghost exposures. But in the CR systems, if you happen to work with a CR system, I think UT still has a CR system, right? So if that machine has not been used in 8 hours, if none of those image receptors have been used in 8 hours, they'll pick up background radiation. It'll just be fog. It'll look like scattered radiation, even if they haven't been exposed. So if you're using that room and it hadn't been used in a while, before you use that room, you need to erase those image receptors. Just send them through the reader. Just send them through the eraser cycle, just to clear them out before you use those. Otherwise, they're going to come out with a lot of fog on them. Okay. And display is just like what we talked about before. It's a resolution of your computer or your, the monitors that they use back in radiologist office. So any questions? We'll see you.